Welcome to section 3. Now that we're familiar with the functor and the ultimate functor we call monad, we're going to look at ways to handle asynchronous code in our functional apps. After all, you can't build a JavaScript app that doesn't have a boatload of async logic, and once again, it'll be a great job for the monad. In this section, we'll start by looking at the promise. It's assumed you know how to use promises already. We'll be taking promises and bending them a little bit so that you can see how they were actually created based on a monad. That will prepare us to look at the functional choice for async functions, which is the future. You'll understand futures a lot quicker after having looked at the similarities between a promise and a monad. I'm so confident that you'll take to it quickly that we're going to do more than just learn the future. We'll write a new feature to our slideshow app that fetches slides from a JSON API using futures. Finally, we'll quickly look at functional reactive streams. These aren't completely functional, but they are another option for working with async logic that mixes well with functional programming. Alright, so let's get started learning how to write asynchronous logic in our functional apps by moving through our first video, which is the promise as a monad. In this video, we'll be looking at the promise, which was actually designed with a monad in mind. Of course, since not everyone knows about functional programming, not everyone knows about monads, the promise was implemented as a hybrid. Certain features smoothed out for convenience, ease of use, or just ease of learning. Very quickly, we'll go over why asynchronous code isn't so easy with functional programming concepts out of the gate, and then we'll modify the promise a little bit to look more like our monad. This should ease the burden when we learn about future in the next video, because we'll be creating a promise that looks almost like a real monad, and the future is basically a promise that actually is a legitimate monad. So let's jump into some illustrations. If we modeled the steps a synchronous program took, it would be sort of like a straight path. We start by doing something in our code. Once that's completed, we can do something else. In this case, it's something... If we modeled the steps a synchronous program took, it would be sort of like a straight path. We start by doing something in our code, and once that's completed, we can do something else. In this case, it's a request to a remote API. So we make the request and then wait. And wait until finally it returns. We can read the response, check for errors maybe, and perhaps map it to a list. Maybe we process that list. Then we're on to doing some other stuff, and so on and so forth. Synchronous code has the benefit that keeping things pure is simple. While reading code, it's easy to know what the state likely is at that part of the program just by looking at it. However, it's inefficient because we stop the whole program to wait for that one thing to happen, that request from the API. Asynchronous code is different in that we start the same way, running something in the code, and then we hit that same API, except we don't wait idly by. We continue through the program doing other stuff and do some other things. Then the request returns, and only then do we read the result, check for errors, map it to a list maybe, process that list. So we get a program that runs faster, things are prioritized, but we get an environment that's more difficult to reason about because we don't know what could happen in the time since our asynchronous request took off till the time it returns. So it's trivial to run into programming errors. Okay, so how is a promise similar to a monad? Well, the first thing we'll need is map, or fmap. Promise has a map function built in. It's just the then function. Then applies a function over the result represented by the promise when it resolves. Next, we'll want to give it an of method. So remember, the of function doesn't check anything. It just returns the applicative type that it's on. So this is on a promise, we will return promise.resolve. Don't do any checks. Let's pause here for a moment. Let's write out some familiar code, familiar to our monad, that is. Take a promise of 25 and then fmap to ramda's add function. And we'll add 30 and then we'll map to the console.log function. Running that, we see that the promise does work like some sort of functor-ish class because it's based off of the monad functor. Let's add app, which takes an apply functor with some value, and it applies that value to our apply functor's function. So in this case, our promises function. So promise prototype AP is a function that takes an apply functor of a value, so a promise that will have a value, and then using fmap or map, we can get the function from this promise. And to apply the value we want, we will fmap it out from its apply functor. However, if this wasn't a promise, this would return nested apply functors because this fmap returns our type class. The inner fmap does the same, so they're both returning a monad or a functor. It doesn't matter here though because the promise unwraps it for us, so we're avoiding those nested containers. Another way we could do this would be with promise.all. Get both this value function and the apply value and map over a function that takes both as arguments. Notice our apt promise works in other ways. We could even use a curried function, like a curried function that takes a user and some posts, then filters those posts to only show ones not created by a user. So if you were on a site, you might not want to see your own posts in your feed. An async function getUser will resolve with a user object with the ID of ID. Our utility function delay will make it more obvious that this is asynchronous. We'll get posts, just a promise with an array of post objects. We app to get users 10, so 10 will be the ID, then app to get posts, and we can see that this works, and it's asynchronous. What about chain? This is the thing about promises. Chain, like fmap, is built into then. So it's built into promise.then. When in fact, promises.then isn't strictly fmap or chain. The promise.then function recursively chains until there's only one promise wrapper. So it's a convenience. Many functional programmers dislike this, but there it is. If we wrote promise.of, 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 promise.of 1000, then fmap that, we're going to get the value 1000 passed to our fmapped function, where if we did that with a regular functor or monad, we would get a bunch of nested functors, sort of like nested Russian dolls. One other thing to note, remember either and maybe? They were basically two monads in one, a left side that meant trouble and a right side that usually meant success. The promise is the same way. It's based on an algebraic data type, except that the promise is a little bit backwards. So .catch could be left map, and .then is like right map. But this can't be strictly true either. .then could be said to be bimap. It works the reverse of how functional programmers expect bimap. It puts left map's function on the right we think of left as bad, right as good. But again, this was designed so that non-functional programmers who didn't really care about the duality of algebraic data types didn't have to learn to put error functions first, or at all. You don't have to put an error handler in every call to .then, as long as you provide something like a .catch at the very end of your promise chain, you're good. Bimap takes two functions, where then takes one or two. So then basically replaces all the different functions that we've learned on the monad. In this video, we basically traced back the lineage of the promise to the monad. Knowing how a promise works, and now knowing how the promise relates to the monad functor, in the next video, we'll use the future monad to build a really cool feature onto our slides app.